I hope you folks are having a good day, morning, or afternoon, wherever you are. So, I think we'll start. So, hi, and thank you for joining me in this webinar again. It'll be a technical deep dive into a PyTorch code sample to unpack Andrej Karpathy's most common neural net mistakes. And I'll be your host. That's me there. And to start, I'll introduce myself. So, hi, I'm Yuval. I've been an engineer for the past 12 years, and during that time, I've worked on some fun projects like StarCraft and a computer vision blood test for malaria. And nowadays, I'm in charge of developer relations at MissingLink.ai, where we make tools like experiment, data, and resource management for deep learning. And these are the tools we'll be using for this webinar. Terminal to launch the script that you can see here at the top, and we'll also be using VS Code to edit our script on the right. And at the bottom left, you see Missing Link, which we'll use to visualize the results in this talk. Missing Link takes care of the ops, so data scientists can focus on the science. And you can imagine it's hard to focus when you're on Twitter all day. There's quite a lot of tweets on absolutely every topic, and sometimes you can find an especially good one. This time it's thanks to Director of AI at Tesla, Andrej Karpathy. So he's in charge of all the neural nets that power the most widely deployed self-driving system. He designed and taught the seminal computer vision course CS231 at Stanford, and you can watch these lectures on YouTube, and I highly recommend you do. And one final note is that this talk is my interpretation of the tweet in question, which is the reason for this talk. Mid-2018, Andrej Karpathy tweeted out quite a bit of sage wisdom for 279 characters. What we're going to do here is explore a specific code sample and go point by point to see how these mistakes can manifest in real code. So this is the table of contents effectively for the talk, and I'll read it out. So the most common neural net mistakes are: 1. You didn't try to overfit a single batch first. 2. You forgot to toggle train or eval mode for the net. Number 3. You forgot to zero grad in PyTorch before backward. And number 4. You passed softmax outputs to a loss that expects raw logits. Now, it'll be about 25 minutes in this presentation, followed by a 10-minute Q&A, and make sure to submit your questions under the Q&A tab, not in chat. So let's dive in. Common mistake number 1, you didn't try to overfit a single batch first. So Andrej says we should overfit a single batch, but why? Well, when you overfit a single batch, you're making sure the architecture works. I've wasted hours training on a giant dataset just to find out it's only 50% accurate because of a minor bug. And the results you'll get are a good guess for the optimal performance of your architecture when it perfectly memorizes the input. And maybe that optimal performance is 0 because an exception gets thrown midway through. But that's fine because we find it out quickly and fix it thanks to it being just a single batch. So now we're convinced that we should overfit on a small batch first. Well, let's, for example, take my dataset here, and I started training my neural network. Let's look at the model that's shaping up. It looks good. Loss is going down. Accuracy is going up. We're at 95% accuracy, and it's still improving, but it's improving very slowly now. And we keep training and training and training up to 99% accuracy. And that squiggly purple line is kind of odd, but you see how it matches the dataset? It wraps around every outlier perfectly. Now, focus on this beautiful spot in the middle. That right there is accuracy and a job well done. Naturally, I got a promotion as a data scientist for this, and after the celebration, I hand the model to my friend Bob, who takes it to production to see some real-life data. And there's a lot of mistakes caused by those little squiggly lines in the model. Remember that red dot with a fancy curve around it? Well, that curve just seems wrong now. My CNN thinks a dog is an ostrich. Why was that dot there in the first place, even? I mean, maybe it's a mistake in the data set that my neural network is now memorizing. Maybe my data set is missing some examples that would prove the squiggly line wrong. Either way, I wish I would have just stopped sooner and taken the simpler model because it generalizes better to the real-world data. But this is the whole data set. Andrej's tweet is saying we should take just a small part of the data set. And just one batch, that's a random subset, so any random subset would do. The main reason we're doing this is to check if the model is capable of doing anything at all. I mean, look at this model. The accuracy and loss are terrible. It's really bad at separating the blue from the red. Luckily, but it's just such a small amount of data, so I can very quickly notice that this model is going nowhere. Now that I know that I have a bug somewhere, I also have a fast way to reproduce the bug, so it's easier to fix it. And looking back at the model that works, another reason to start with a small batch is that generally, adding data points makes it harder to fit. So in this exercise, we get an upper bound on the potential performance of the architecture. So that's why you would overfit a single batch. Now, how would you go about doing that? Well, in PyTorch datasets, you're usually iterating over a data loader. So your first attempt would be to just index it and try to get the first item in the list with the 0 index, but you'll immediately see that there's an error thrown, the type error, because the way train loaders are set up, they don't have the index operation. That's because they might have a data set that's remote over the network, and you maybe want to have an infinite data set. There's other scenarios that they just don't want to support this indexing feature. So your next best instinct might be to try to convert it to a list, because the list does support indexing. But that means you're going to evaluate the entire data set, which is going to burn your time and memory. So what else can we do? Well, in Python, a for loop like this, for item and iterable, and then do stuff with it, it's pretty much the exact same thing as what you see on the right. Calling the iter function to create an iterator, and then calling next multiple times on that iterator until we're done when a stop iteration is raised. So in that loop, we'll just call next, next, next. So if we just want to get the first thing out of the iterable, we can do the same trick, but we only call next once. So we do iter to get the iterable, and then next, and you notice I assigned that into a variable called first. In PyTorch, this is what the training loop often looks like. So to get the first batch, we'll replace this with that next iter trick. You can see I assigned the next iter into a variable called first batch. Then, to iterate, I made it look like I have 50 copies of this batch. And an alternative would be to use a while loop if you want it to go on forever, but I wanted to compare specific experiment links, so I multiplied the batch by 50. And now I'm going to jump into some code. So just so you know, it is an MNIST example, the hello world of deep learning. And this is the general code structure. At the top there's going to be the imports, then the constants, the neural network architecture, followed by functions, and finally the main function. So let's go into the code. We're going to jump into Visual Studio Code right now. So here we are. You should be a little bit familiar. So here's the imports, the constants, and the neural network architecture that we're going to be using is this right here. So you can see that we have, in the features, we have a convolution, max pool, and a ReLU. Then another convolution, a dropout, a max pool, and a ReLU. And followed by two fully connected layers. So we have a linear, ReLU, another dropout, another linear layer, and finally a log softmax. And in the feed forward, we basically do the features, convert the view to the fully connected view, and then use the classifier, so the fully connected layers, and return the output from that. That's pretty much all I wanted to show you at this part. And in the main function at the bottom, what we're doing here is you'll see I'm getting that first batch, just like we did in this, just like I showed in the slides, with the next iter trick. And what I'm doing with that first batch is, you can see here, I'm multiplying it by 50 to get a fixed size and overfit over this first batch. And I have this train function in which I'm actually putting in the model, the optimizer, the epoch index, and then what I'm doing with this is actually the training data set, followed by the validation data set. So you can see if I comment this thing out, and I can use the bottom one, this is actually training over the entire training loader with the entire test loader. Or I have this other variation where I'm overfitting the training, but I'm actually using the full test loader. This may take more time, and in this version, I'm just taking the first batch of the test loader and overfitting over the 50 copies of the first batch. So you see, I have all these configurations where I can use to run this multiple times in various ways. And you can see here, I just alt-tabbed into missing link. So you can see this visualization from 4 days ago, where you can see the x-axis is the iteration number, the y-axis is accuracy, and I can choose other variations of that. Now, it took me 4 days ago, 16 minutes, to realize that this looks maybe okay, but there's these weird dips or negative spikes in the data, and I'm scratching my head thinking, what's going on here? So I'm going to try and run this again with the very short 50 copies of the first batch. So I'll go into my terminal, I'll launch that, go back to missing link, and in the dashboard I can see. So I'm glad we can see the dips or spikes in this case too, so we can quickly debug the problem. That's a good example of why it's valuable to test by overfitting a single batch. I just reproduced the exact same problem without waiting the whole 16 minutes. I just did it in 10 seconds about. We'll debug that issue in just a moment, don't worry. I want to jump right back into the next most common mistake. Number 2. You forgot to toggle train or eval mode for the net. So why does PyTorch care for when we're training the model versus when we're evaluating? Why do we have to toggle between these different modes? And a big reason for that is dropout. This technique randomly removes neurons during training. The idea is that this removes crutches that the network is relying on. I mean, imagine if these red neurons in the picture here, if they were the only ones that were contributing to arriving at a correct result. Well, once we remove the red neurons, it forces the other neurons to train and learn how to be accurate without the reds. So this is the big idea behind dropout. And this dropout improves performance on the eventual test, but it very negatively affects performance during training because the neural network is effectively limping. I mean, it's going to be missing parts that it needs to be accurate. So let's take a closer look at the code and see what's going on there. So I showed you this train function before, and if I dive into it, well, you can see my parameters, and you can see that immediately in my train function, I'm calling model.train to tell PyTorch, hey, I'm training right now. So in dropout, you're going to drop a few neurons here and there. And then I'm doing the inference step and 0 grad, so I'm updating my weights. And here, once in a while, I'm doing a validation. So with the validation, I run this test function here. In that test function, you can see it sets model.eval. So during the test, we don't want the dropout to happen because we want to evaluate what's the actual performance of the network. And if we go back, I think we might be able to notice the problem. So what's going on here is this loop for each batch is going to be training with the model.train set at the beginning. But then we're going to set in this test function, we're going to set, once in a while, we're going to test this, we're going to set the model.eval mode. And if we iterate again inside the loop, we will not be calling model.train. So we're in this perpetual test mode. And that's why we're seeing those spikes, because the model once per epoch was getting that model.train and getting dropout, whereas in all the other scenarios, there was no dropout. So it was just an inconsistent level of dropout. And if we try this out, if we try this out and put model.train within the loop, so it always gets called right before we do our training, let's try and run that again. I'll switch to missing link. And the spikes are gone. So another thing you might notice here as well is in this chart where we're looking at accuracy, now the blue is training and the yellow is validation. The training is performing worse than the validation, which might cause you to scratch your head to begin with, but when you're thinking about dropout, this is exactly what we expect, because this is the limping neural network with missing parts of it. So we're expecting to see this exactly like this, so that the training is doing worse. So that's what you'd expect to see in the case where you forgot or you somehow mishandled trainer and eval mode. You might see spikes in certain parts, or you might see just other deteriorations, and there are other scenarios where this might happen, so just be very careful. And this brings us to common mistake number 3. You forgot to 0 grad in PyTorch before backward. And we'll start with backward and then come back to 0 grad. So imagine you just called backward on the loss tensor. You're telling PyTorch to go back up the graph from the loss and calculate how each weight affects the loss. That's the gradient for each node of the computational graph. And using this gradient, we can optimally update the weights. Now, going left in this illustration is what is going on with the backward. And if we focus on one of these nodes, we'll notice that there's multiple inputs that are flowing back into the gradient of that node. And this example node will accumulate all these gradients. I mean, it's going to not want to calculate all these separately and apply them separately. What PyTorch is going to do is it's going to sum them all up, all the different changes in how they're affecting this node. And that way the node will get the final sum total gradient that it deserves to update. And this is what it looks like in code. The step method there is, at the end, we'll update the weights based on the results from the backward step. And what might not be obvious in this code sample is that if we keep doing this over and over and over many batches, the gradient will explode. So the step we take will keep growing and growing and growing. And that's why PyTorch requires us that we add this explicit 0 grad in between. And that resets the gradients back to 0. And one way to make sure you didn't fudge this is to always have these 3 functions go together. 0 grad, then backward, and then step. Now, we'll jump right back into the code to see what happens in an example scenario if we forgot to 0 grad. And I'll go back to the terminal to run this code again and jump right back to missing link to see how that pans out. Now, you can use missing link for visualizations. You can also use Visdom or TensorBoard. You can see some stuff that you can get out of missing link. Like, one cool feature is that it actually saves the exact code of what I'm running, and you can see some hyperparameters too. Now, we can already see something that's going on here. Like, we shot up in performance to 80% very quickly, and then crashed way back down to 10% accuracy, and from there we never recover. So what's going on here is at the start the gradients are updating correctly the weights, but then the gradient keeps growing and growing, and the updates become pure garbage, and we get further and further away from a valuable solution. So this is a pretty good proof for why you should be careful and don't lose your 0 grad. Make sure it's always happening. So I'll quickly go back and uncomment it because that makes me uneasy. So this is the example we just saw when 0 grad is missing, but you can also do other mistakes like put the 0 grad right after the backward, effectively erasing the gradient that you're just trying to create, and then what happens is nothing happens. The weights just never update. So your validation performance is all the same, and the only variation you're going to see is when there's dropout or other random variations in the training. At this point, you might be wondering, why not just combine these operations into one? I mean, they seem to always have to go together, and I would mostly agree. I mean, but then would you make 0 grad immediately call backward, or maybe each time you do optimizer.step, right after you do 0 grad? So which operation should be united into one? Or maybe you should have just one operation that does all 3 together. One method on your model that 0 grads calls loss backward and then the optimizer step. Well, maybe it should have been a triple operation, but right now PyTorch demands that you keep them separated, and it's nice that it is explicit so we know exactly what's going on with the gradients when they're 0 and when they're not. And I did try to find a real-life code sample that made it necessary to keep 0 grad completely separate. I didn't find one, so if anyone has a link, please shoot it my way. I mean, a reason to keep 0 grad separate, for example, would be to call backward multiple times for each time you call step. So for example, if you can only fit one sample into memory per batch, and then one gradient would be too noisy, and you'd want to aggregate a few gradients per step, but even then, maybe the 0 grad should have just been part of the step. And another example you might think of is that calling backward on different parts of the graph might be useful, but in that case, you might as well just add up these parts you want to call backward on, and just call backward on the sum. So I don't see a really good reason for this yet, but I would love to be enlightened. So with that, we'll jump right into common mistake number 4. You passed softmaxed outputs to a loss that expects raw logits. So first of all, what is this? Well, logits this is just a common neural network. What you're seeing here, you see the input, the conv networks, and then some pooling, and at the end, fully connected layers. So the logits are the last fully connected layer, and the softmax is just the same activations of the last fully connected layer, but after some normalization. It really is the same thing. If you look here at the top, I have actual real-life numbers that came out of the code sample that we just saw. This at the top is the logits, and right after that is the log softmax. And if you look at this bar chart, they're practically the same. The only difference is the scale. But because of this subtle difference, all the math breaks apart. I mean, notice that the top has the logits, they have some positive values, whereas the log softmax, they're all negative. So before we jump into an example of how this all breaks apart, why is it such a common mistake that this happens so often? Well, this is the PyTorch official MNIST example. I mean, look at this forward method. Notice the first line is a conv, a relu, and then a maxpool2d, and at the end, right before the end, you see there's a last fully connected layer and a log softmax. Now, this is the MNIST example. Every single PyTorch beginner will go through this code and see that log softmax. But then, when you look at the official PyTorch ResNet or AlexNet models, you'll see they don't have a softmax at the end. They send out the raw fully connected layer. They send out the logits. Now, you'd think this difference would be clarified in the docs. But here, for example, is a function called NLLloss, very commonly used. There's no mention whether its input should be logits or a softmax. So your only hope is the code sample, in which you see here at the bottom that NLLloss, it takes in a log softmax. I mean, if somebody here on the line has some time, this might be a very useful pull request, just to go through the entirety of the docs, find out all the loss functions, and define exactly what they expect to be in the input, and also for the models to explain as well what is coming out of them in the output. But until the docs are good, or maybe even renaming functions to make it clear with that, or some type system, until that day, what I recommend right now is to just always look at the code samples and look at the actual code of the models to make sure you know what's coming out and what you need to push in. Let's jump into some code that'll show this problem. So what I'm going to do right now in VS Code, I will go back to our neural network architecture right here, and all I'm going to do is comment out the log softmax. So it's kind of the opposite mistake. We're going to output logits, and it's going to go into our loss that is expecting a softmax. And when I run it, I'll go back into missing link to see the results of that experiment. And this is pretty weak. So you can see that we got some 20% accuracy and then nothing. Not even noise. It's just completely broken. So if I go back to the terminal, I'll see, and you can look at the logs at missing link as well, but you can see that there's nans in the loss. So those positive numbers completely confuse the system, and you can't differentiate, you can't get a gradient out of nans. So completely broken. Again, I'll undo that. So we saw an example on why it's super important to make sure you're aware of when it's a logit versus when it's a softmax. And I'd like to thank you for joining me today, and also make sure to check out these resources if you want to follow up and see more tricks on how you can debug neural networks. So in the first one, there's a few rules of thumb for what kind of numbers to expect and a few visualizations. And the second link is a longer blog post that expands to 37 reasons why your neural network might be broken. It's really good stuff. And the third link is where you can find the code I used for this presentation. And with that, I'd like to say thank you for joining me today. Make sure to shoot me an email or connect with me on Twitter if you have any questions. We didn't go into the number 5 and number 6 mistakes that Andrej mentioned. I mean, we'll save those for another time. If you ever run a deep learning experiment, it really helps to visualize your results. And I'll show one last thing. For example, I'll go to missing link, and what we'll do right now is compare the recent models that we trained. I'll go on it per batch, and I'll look at the accuracy for validation. And you can see here that there's the red one that ran for a very long time, but we can already tell that the best accuracy was in experiment number 118. And I can even go here from column 118 directly to the code of that experiment and utilize that one. I'd like to say, yeah, what we're going to do right now is, before you folks leave, we'll do a quick Q&A. So again, thank you for joining for now, and I'll just read up on the questions real quick. Hope this webcam works. So I'll publish the questions that were asked here. Okay, great. These are great questions. So first thing, maybe I'll push out the code, the recent version of it, so you guys can immediately access it. And I'll paste the link in chat as well to make it easy for you folks to see it. So pushed it out, and this is the link in the chat. It's coming right up. And one thing to note, that we will be publishing the slides. I saw that question in chat too. And there's some citations you'll find in the speaker notes. Some of those visualizations were crafted by myself. Some of them were used from other resources. So you can find those links and other resources in the slide. And I'll jump right into the questions. Okay, you're asking a question in the chat. That's fine. It's easier for me to follow in the Q&A section, but I'll try to answer those as well. So first question, is the missing link console for visualization free? And the answer to that is it's free for trying out if you're using it in a company setting with multiple data scientists, and there's more features there like controlling version control for data. And we have a really easy way to manage your cloud or on-prem GPUs. If you want to use more of the more pro features, that costs money, but just to track your experiments, that is free. So that's the answer to the first question. Next one. When do you stop overfitting on a single batch? That goes way to the beginning of the slide. Well, really, it's a tool for debugging. So mainly when you're going to overfit a single batch just when you're trying a new change, a new different architecture, or just tweaking things that you think might break. And when you want to stop doing that is when you want to go to production, when you want to get real numbers for your performance, or you're going to train over the whole thing, and just basically before deploy. And next question, why do the big PyTorch models send out logits? So the answer to that, we saw ResNet and AlexNet, in PyTorch, they have logits as the output instead of the softmax. And the reason is you might want to do transfer learning, and you might want to do other things with the logits. You want to modify that. So, and you might want to use a different loss function because you want to do different kind of fine tuning. So it's redundant and maybe too opinionated to decide on a softmax for those. And that's the main reason. So it's just to be more generic. They don't include that in the real packaged Torch Vision models. That's as far as I'm aware. And there's new questions. So how to check for gradient explosion in neural networks with PyTorch. So gradient explosion, I guess one way to do it is you can track metrics. And one of the metrics you can track is the size of the gradient. So you can actually look at the gradient vectors or matrix and tensor, and then take the magnitude of that tensor. And some folks use that as well for evaluating a different kind of loss, but you can just add it as another metric that you're tracking. It's kind of easy on Missing Link, and you'll see a chart as you iterate what is the size of the gradient, which is actually a really cool trick that I think it's fun to look at. And another question we have here, when is the next webinar coming? Good question. So I don't know the answer to that. I think we have one scheduled for about a month from now, but not final yet. Definitely look at this channel. So it's at bigmarker.com/missinglink-AI. Make sure to check that out, and I think you can subscribe there to updates for more webinars, and also follow us on Twitter. It's missinglink-AI on Twitter. So make sure to follow us on those channels, and you'll be able to keep up. Next question is, which of these mistakes apply to TensorFlow, Keras, and other frameworks? Okay, so yeah, Keras and TensorFlow, you can control the gradient when it's being zeroed or not, but usually you wouldn't do that. I think that one, zero grad, is not as relevant. I guess the most important one is before you do anything, always overfit on a single batch to see what's going on there. That's the first mistake, and that's why it's the first one. It's the biggest, most useful tool. So that's the biggest mistake that's translatable to other frameworks. And in the future, next question is the future webinar going to cover points 5 and 6? And the answer to that is maybe. I think actually we might be doing a webinar on super resolution, like how do you take an image that's low res and then using some cool networks to make it very detailed. But TBD, we'll have an update on the channel, so follow us on Twitter and on BigMarker for knowing further webinar info. And next up is follow up on my previous question. Can gradients for all the nodes be tracked with missing link? So we do offer a thing called artifacts. So if you write a file to /output, any kind of output can be saved. And that includes checkpoints for your weights is what you usually save and track. But if you want to actually track the full tensor, the data that's behind your gradients, well, you could output those as well. Those are fickle though. You generally, they get replaced every batch. Though maybe, so as a metric, if you were just to track the magnitude of the gradient, that might already be something useful that you can very easily chart because it's just a number, the size of the gradient. And then you can see that over time, what's going on. And I guess with dynamic learning rate, you'd expect the learning rate to become smaller, and maybe even the gradient becomes smaller because you're closer to that optimum. So that could be a useful thing to track as the number, but the whole weights. So again, you could track it with files, but I don't know if you'll find value in having the full gradient stored for it. Maybe if you want to debug something, maybe. So next question here is how to get comfortable with the C++ API of PyTorch. Well, I myself have not used the C++ API of PyTorch, so I'll have to get back to you on that, but that's a really good idea for maybe a future webinar after I get some mileage on that one. So thank you for that. And I'm looking at the chat now. Super resolution webinar would be cool. Yes, super resolution, you're all into it. Awesome, I'll follow up. So thank you. Yeah, you're welcome for the answers, and thank you for the questions. And again, thank you for stopping by. This was awesome. I had a lot of fun, and I'll see you folks next time. Make sure to go to missinglink.ai to sign up for your free account today. See ya, folks.